So we'd like to finish this session of talks with Andrew McDonald, who's going to talk to us about the space-time variability.
I was taking it.
Oh, okay. Is Jim also talking too? Okay, thank you very much. This was the team of participants in the workshop that we held earlier this winter. And among the conversations that came out, we utilized this stack of sticky notes to assemble our thoughts and bring together our different input and sort of sort out how these different things interacted. One of the things we didn't anticipate was the fact that the sticky notes didn't stick to the glossy wallpaper in the hotel conference room. But we worked it out, and we were able to arrive at these three major all-encompassing topic areas that Adrian pointed out earlier. And the first two speakers really hit on the dissolved particulate continuum and processes related to the food web regulation of export. One of the subjects that kept coming up, and it was difficult to, in some ways, to set it aside as its own thing because it was so integrated with the other topics and priorities, was this variability in space and time. And among those, in that category, that broader category, we identified the priority areas for future research being, one, episodic events of particulate matter fluxes, and also just the general and large scale and all range of scales of patterns and of temporal and spatial variability in the biological pump. Both of these things need more attention as we go forward. So my goal here today is just kind of give you, I can't go through every single subject related to these, but I'm just going to give you some examples and try to put some perspective on where this leaves us and where we might take these in the future. So in terms of episodic events, we know that we've observed rather fortuitously, oftentimes, events of jelly falls reaching the seafloor, such as the Sweetman and Chapman observations, and their understanding of what they can contribute to the particle flux. We can see on the right phytodetritus on the bottom, as well as mixed in with other jelly falls. And then we can observe sometimes you go out in, for example, the Western Antarctic Peninsula with Debbie and her crew, and one net comes up empty, and then you move to the next station, and then you've got buckets and buckets full of salps. And these different components are rather intriguing, and we don't have a good understanding of how they operate, how they affect the system, and what their overall contributions are to the biological carbon pump. So in terms of the spatial and observations of where photodetritus, for example, it's been found throughout the globe, but at stations that have been visited before, so we don't really have any idea what's going on in the rest of the oceans. Does this process actually extend out into the other regions, or is it something limited? And what is the scale, spatial and temporal scales upon which those happen? And what are the magnitudes of the carbon and other elements that are associated with these fluxes and these events of phytodetritus found directly on the seafloor? Stone and Steinberg did a series of studies where they looked at salp biomass variability and its influence on particulate fluxes at the BAT site. This is the time series with the months on the vertical axis and then the years on the horizontal axis, displaying the variability that they found in the long-term record of salp abundance and biomass at the BAT site. And what you can see here is this, this scale bar ranges many orders of magnitude. And so it can be quite patchy, and we can see all of a sudden these large events showing up that have the potential to graze a lot of material from the water and contribute to the overall flux in terms of settling of carcasses, the migration, and also the production of fecal pellets. So in this follow-on paper, they modeled this, this process and the contribution of these salps to the total flux at the bat site. And what we can see is that the indications are that the spikes in flux that we see in the record are in large part due to these contributions from the salps. And when we look at their effect on grazing, in addition, we've got the chlorophyll abundance or biomass in the upper blue line, and then the salp grazing, modeled grazing rates in the black curves below that. And we can see that there's a lot of variability from each time they go back out to sample and what that imparts on the model. And at times, even the grazing rates are grazing more than the standing stocks of chlorophyll. One interesting question is when we think about this in terms of how do we detect this? How do we understand what's going on and what are the scales of this? Are these spikes having an impact on the overall chlorophyll distributions? Are these something that are detectable from from space, for example, from satellites? It remains an open and challenging question to address. So some of the priorities outlined and agreed upon by this workshop, by the participants, was what is the frequency, intensity, and spatial scale of these episodic export events across the globe. This is something that we really don't have a good handle on, and was one of the primary outcomes that we need to invest in terms of our future research efforts. And how might we better observe these events? Right now it's been mostly fortuitous through time series observations at a few sites, but really in order to understand the first question or answer the first question, we need better tools, and we need to better apply these tools more prolifically in order to capture them. Thirdly, what are the ecosystem traits and environmental conditions that lend themselves to the generation of these episodic events? So what's behind all these? What's controlling these? And these relate, this tied in with these other questions of food web characteristics that was also identified as the top priority in our understanding, in investing in our understanding. And what is the ultimate fate of this material, and what controls it? Is this material attenuated differently than the typical organic matter that's sinking out of the euphotic zone? And does it behave differently? Does it end up in a different place? Does it have a different impact on the ecosystem and biogeochemistry? And finally, how do these episodic events structure the ecosystems in which they occur? So moving on to the second major topic, the patterns and scales of spatial and temporal and spatial variability. Some of the key things here: what tools and approaches are needed to assess the variability across all relevant scales? What can we apply to the problem? Similar to the previous question. How do food web processes structure the spatial and temporal variability in organic matter flux? Again, relating to these overarching priorities defined in the other major categories. And how might these patterns be responsive to climate change or other changes that happen on a variety of scales, of time scales? We can look at short-term variability with some of the tools we have, for example, optical profiling floats, such as this one developed by Dave Checkley. And we can see over a time period of a few days and depth on this axis, and then the concentration or beam attenuation of particles in the water we can see the patterns and how they evolved over time with respect to each day and time of day, and with respect to depth. And so this is a highly dynamic system that we're only able to capture with new techniques and new observation tools that are allowing us to sample at these smaller scales. Shifting the focus more to the global perspective, Scott Doney showed this, this plot from Charlotte's paper that's in review in Biogeoscience Discussions. But there's large variability in the model-based assessments or estimates of export production, and also the more observationally based, but still kind of model-based, combination of model and observation-based assessments of Henson and Dune. And so there's huge variability here, and so we don't really understand what is the spatial pattern and what controls these spatial patterns throughout the oceans, because the tools that we've applied to address the problem are largely insufficient to really fill in this total picture. Here's one of the data sets. This is that Henson et al. Used. It's a combination of sediment trap data and thorium data. And while there is coverage in the different ocean basins, there are large sections of the oceans that are without data, and we don't really have a good understanding or a good way to compare these models to the observations and make them better, as Scott was kind of saying. So if we're honest with ourselves, and the modelers, they have been very honest, and they talk about it, for example, definite interpretation is not straightforward because of heterogeneous data distribution and methodology. We need more. We need to do this better in order for them to be able to use these tools to answer these questions. Or Yvonne's paper, the sparseness and relatively large uncertainties of sediment trap data makes it difficult to accurately evaluate the skill of the model and other parameterizations. So we don't even know if the mechanisms behind these models are running correctly, and we can't really assess what's going on in terms of export and flux through the water column. And that problem is really amplified in the mesopelagic zone, where we have even fewer observations. And we see the sort of differing pictures that we get from the variability in attenuation, almost opposite patterns that we get from different approaches to addressing the same question. And this is important because we need to be able to take these understandings that we have of the current system and be able to apply it to future progressions. Scott also showed this other figure from Charlotte's paper that shows a few different models and the changes in export production that are going to happen, that are modeled to happen under RCP 8.5 by the end of the century. And the spatial patterns, again, the spatial patterns here are really quite different, and they don't, we need to be able to constrain what we know now, and in order to better understand what the changes are going to be in the future. So I wanted to kind of bring this into perspective and give you a little bit of an analogy as to where we stand in terms of what is the state of our current observations and where might we go in the future trajectory here. If we look if we use ocean temperature as a basis for that, starting with the Challenger expedition in the 1870s, got a nice transects across the globe with some subsurface temperature measurements. By 1934, technology was changing. The reversing thermometer and Nansen bottles were employed. By the 60s, we had CTDs coming on and helping us fill in subsurface measurements of temperature. And by the 80s, we've got expendable bathythermographs that are giving us better understanding of the temperature. And then finally, by 2015, we've got now 1.5 million profiles and counting of temperature with the latest technology. And I think this is important to sort of put it in perspective in terms of our understanding of the spatial variability of the biological pump, because these data sets, even this year, we're still relying on the Challenger data to sort of tell us about how these changes have occurred over the last century. And so some of the biggest understanding in terms of the changes in heat in the oceans have come because of these early data sets. And so if we put this all on a timeline, we've got the temperature timeline and progression of observations up there, and we've got the biological pump observations down here. We're still kind of stuck back in the 1930s or something in terms of our spatial understanding of what's going on. And so this is starting to change because we can apply all the technology and advancements that have happened in the meantime and pretty rapidly advance this field and expand our observations. The French, for example, are doing this very elegantly, of course, with their observations in the sailboat throughout on the Terra Oceans expedition, sailing and getting about 150 different stations throughout the globe, using the underwater vision profiler combined with the genomic assessments and understanding the fluxes in the upper 500 meters or so, fluxes with this flux proxy at least, of the patterns and linkages between biology and the particles that are through the water column. Earlier last year, I participated in the P16 North repeat hydrography cruise, and by integrating the same instrument, the UVP right there in the center, with these hydrographic rosettes, we're able to really match the hydrographic scales of the large-scale hydrography programs and start to get an understanding of the total abundance of particles. So this is the number of particles per liter observed by these optical measurements. And we see, very similar to what Monica actually showed, is these patterns of deep penetration of particles at the equator and big penetration, again, at the boundary between the subtropical and subpolar gyres in the North Pacific. There's a lot of interesting features here that we can discern from these large-scale patterns and make advancements of our understanding of how the biological pump is working in these different regimes. One of the things that came out of it is I'm looking at these data. We've got concentration in terms of the number of particles and concentration in terms of the particle volume in the center and the mean particle size. And we can sort of sort out these different vertical regimes. And one of the features that really stood out to me is the widespread pattern or presence of this mesopelagic particle maximum. In this case, occurring in this example at the subpolar subtropical gyre boundary, occurring down at 200 to 250 meters in depth. And I believe this is an indication, and using these optical tools, we can start to diagnose the patterns that are going on here and look at maybe this is the presence of processes such as disaggregation or fragmentation acting on taking large particles and turning them into small particles. And that matches with the distributions of size and overall concentration. In addition, most of the previous studies with the UVP have really focused on size distribution, but we can also get information such as what types of particles these are. And so we can sort these into different functional groups even of aggregates such as these. We can look at fecal pellets, or we can look at the classes of zooplankton such as the copepods here. And so really the opportunity is ripe for taking these observations and really extending them to the global scale. We're getting there. This is the latest compilation of measurements from Marc Pickerel's group in France. And they have, our coverage with optical instruments is getting better. A lot of these are not full depth. And you can see there's the P16 North line on the left there. But there's also the opportunity to really expand these, for example, with all the ongoing global hydrography, and get a better understanding more data points to be able to test the processes and dynamics that are governing the models, and so we can test our understanding of the spatial and temporal variability in the systems. In the same way that we've learned a lot from matching DOC with these hydrographic scales of sampling. We've learned a lot about the cycling and of this very active organic pool. Just to briefly go through a couple of other tools that are at our disposal, we've got imaging, the imaging flow cytobot. We can catch this biology on camera, look at the spatial and temporal, or the temporal, high-resolution temporal patterns of individual members of those communities. And that's giving us new insights into these community structure, food web type aspects and what's going on. We've got new genomic tools and automatic sampling processes that can help us pull these out and identify gene pathways and features of the community there. Acoustic tools can be applied on global scales to be used to map out abundances of zooplankton, or in this case, mesopelagic fish, helping us understand and put bounds on what is the large-scale variability of these and influence of these very important, potentially very important elements of the biological pump. We can fine-tune that down to smaller scales by merging acoustic or even optical techniques with our latest fleet of autonomous sampling devices or platforms, such as this acoustic, glider-mounted acoustics by Powell and Oman, where they looked at the diel vertical migration patterns across this front that happened right here. And you can see that there's very different magnitude, or really a loss of the diel vertical migration patterns on that one side of these very small features. So understanding those and looking at the effects of this on the biological pump is another necessity. And then there's been a lot of developments as well in terms of using optical tools, such as the stuff that Jim's going to talk about, and Meg have been developing these in situ optical tools to use them really as a proxy for assessing the temporal and spatial variability in flux at new scales that we haven't been able to do prior to these tools coming around. And so really there's, in addition to the hydrography, there's other platforms that are available to really expand our understanding. We've got floats that we can equip with bio-optical sensors. And so an expansion of the Southern Ocean program that's spinning up now would yield a large insights into this variability. The PACE mission, obviously, as we discussed before. And then the time series sites associated with the ocean observatories really offer a platform for us to utilize to get a process-based understanding and a time series look at what's going on in the system, and really try to really quickly move from that 1930s understanding that we have of the biological pump in terms of the temperature analogy, and move it into the modern day. And so there's a bunch of open questions. There's need for intercomparison between these methods, these new tools, calibration and verification. One question that I struggle with a lot is, are these observational proxies for flux sufficient? Are they, a lot of times we're basing them off of sediment trap calibrations that themselves have problems. And so to what extent are we going to be able to trust and utilize and learn from these proxies? Maybe not necessarily, we're not going to know the exact number of milligrams of carbon per meter squared at that one particular location, but at least we'll be able to start relating these broad patterns with the overall ecosystem and food web processes that we're starting to investigate. Achieving new understanding through combining multiple approaches. How can we use these tools to scale up to obtain global observational coverage? And how are we going to track change in the biological carbon pump over long time scales? Which parameters are we going to use? Which platforms? And are these flux measurements that we're making, are they really climate quality that we can trust to detect trends? Or are they really just kind of telling us about the oceanographic weather of flux patterns that are going on at any given location? All right, that's all I have.